Hello viewers, we will discuss contour integration in this session. So, last time we defined what a contour is. It is a join of piecewise smooth curves over some parametric interval, and we are going to use those contours to define a line integral of some sort for complex valued functions. Okay, so, here is contour integration. So, let gamma be a contour in C with in C, this is the complex plane C with parameter interval a b, okay, and let f from gamma star, remember that is the range set of the contour gamma. Okay. So, f from gamma star to C be a continuous complex function. Okay. So, then define so this symbol I will call this the contour integral of f over gamma, okay, as well. This is the notation, the contour integration of f over gamma is equal to the integration over this interval a b of f of gamma of t times gamma prime of t dt. Okay. And the right hand side here is actually an integral of the sort we have seen in the last session, where okay, so f of gamma of t times gamma prime of t, okay, is essentially a complex valued function, okay, in the with a real parameter t, okay, and we have integrated such functions in the last session. Okay. So, the right hand side integral, in the right hand side integral, gamma prime may not be defined at all places. So, we will assume for this definition that gamma is a smooth contour. So, please allow me to make the change, let gamma be a smooth contour. So, if gamma is not smooth all over, okay, so if it is piecewise smooth like we have in a general case, then we would define this integral to be summation over specific intervals, okay, and we break this interval a b into intervals where gamma is smooth. Okay. So, what I mean by that is suppose gamma is a piecewise smooth contour on okay, with the parameter interval a b, okay, and suppose that there are n points. Okay. So, suppose that gamma is smooth on a t 1 comma a t 1 t 2 etcetera t n comma b, let us say, okay, where these points a strictly less than t 1 strictly less than t 2 t n strictly less than b. Okay. So, this is how a piecewise smooth contour will look like. It's smooth on pieces like that, on pieces of this interval. Okay. Then in this case define then this integration this contour integration f over gamma is defined as the summation. Okay, well, I haven't written in this. Yeah. Okay, so I will write T0 to be A, okay, and Tn plus 1 to be B for convenience. Okay. So, then I can write summation k equals 0 to n plus 1, okay, of the integration from Tk. Okay. So, this summation will run only until n, okay, Tk to Tk plus 1 of f of gamma of t, gamma prime of t dt. Okay. And now, we do not have problem because gamma prime is defined on all of these intervals. Okay. It is piecewise smooth. So, on each of these intervals gamma prime is smooth, or gamma is smooth rather. Okay. So, we can define the contour integration in a modified fashion like this for piecewise smooth contours. Okay. So, let us see some examples. Let us see how to calculate a contour integration in some cases. Okay. So, here is the first example. Let gamma of t be the curve, be the contour e power I t 0 less than or equal to t less than or equal to 2 pi. So, this is the unit circle, okay, parameterized in that fashion, in the standard fashion, okay, and let f of z equals z squared. Okay. This is for all z. Okay. So, in particular this function is continuous on the range of the contour, namely the unit circle. This is actually analytic function all over C. It is an entire function. So, it is definitely continuous over this contour. Okay. So, we can compute. So, compute the contour integration of f over the given contour. Okay. So, we can compute this. This by definition is the integration, okay, over this interval, parametric interval 0 to 2 pi of f of e power I t, okay, and then gamma prime is I e power I t. The differentiation of e power I t is I e power I t, and then we have a dt. Okay. So, this gives us well, f of e power I t, f of z is z squared. So, f of e power I t is e power I t squared, which is e power 2 I t, okay, times I e power I t dt. Okay. So, we get integration from 0 to 2 pi of I e raised to 3 I t dt, okay, which I am going to write as integration from 0 to 2 pi of I times cos 3 t plus I sin 3 t, okay, dt, and multiply the I, you get integration from 0 to 2 pi of minus sin 3 t plus I times cosine 3 t dt. Okay. So, now the integrand is a real parameter function, okay, and it is complex valued, okay, and we have seen how to integrate such a function. You just separate it into it is integrated by separating it into the real and imaginary parts. So, you get integration from 0 to 2 pi of minus sin 3 t dt plus I times integration from 0 to 2 pi of cos 3 t dt, okay, which is clearly 0. Okay. Okay. So, that is how we compute these integrals, okay. And there are, well, let us actually see one more example. So, this is in some sense the fundamental integral. Okay. This example is very important, it keeps coming back to us again and again. Okay. So, we will use this very much. So, it is an important example. Let f of z equal z power n. Okay. So, essentially it is the previous example with z power n instead of z squared. Okay. So, let f of z be z power n, n is any integer, z not equal to 0 if n is strictly less than 0, but that does not matter for us. Let gamma of t be your unit circle parameterized as before, or we can actually take a circle of radius r, where r is positive, 0 less than or equal to. So, let me write the gamma of t is r e power I t, 0 less than or equal to t less than or equal to pi. Okay. So, this is a circle of radius r, r is a positive real number. Okay. So, compute well, since r is positive real number, f is definitely defined there on the range of gamma, and also it is continuous there, it is actually analytic on gamma. Okay. So, compute the contour integral of f over the contour gamma. Okay. So, this is the integration of r raised to r e power I t raised to n, z raised to n, z comes from the contour. So, gamma of t raised to n, and then times gamma prime of t, gamma prime is r I e raised to I t, and then a dt, and the parameter interval is 0 to pi. I apologize, this should be the circle 2 pi. Okay. So, the contour visually is a circle of radius r, centered at the origin. It starts at r, and ends at the same real number. It goes in the counterclockwise direction and ends at the same real number r. And the calculation is very similar. So, you get r power n plus 1 r power n plus 1 integration from 0 to 2 pi, and then you have a I, and then you have e power I times n plus 1 t dt, e power I n t from in here, and then 1 e power I t from here. So, you get well, let me write e power I n plus 1 t as cos n plus 1 t times sin plus I times sin n plus 1 t like before. So, I get integration from 0 to 2 pi of r power n plus 1 times I times cos n plus 1 t plus I sin n plus 1 t dt. So, this gives me integration from 0 to 2 pi, and the real part is minus r power n plus 1 sin n plus 1 t dt, and then plus I times integration from 0 to 2 pi of r power n plus 1 cosine n plus 1 t dt. So, this is minus r power n plus 1. If so, I will split this into cases. If n is not equal to minus 1, so case 1, If n is not equal to minus 1, in this case you can integrate okay, you can integrate this piece to get minus r power n plus 1. Well, the integration of sine is negative cosine. So, I get plus cosine n plus 1 t divided by n plus 1 and then between 0 and 2 pi. Okay. And that's clearly a 0 plus I times likewise r power n plus 1 sine, the integration of cosine is sine n plus 1 t divided by n plus 1 between 0 to pi. Okay, and that is also a 0. So, the integration is 0. Okay. And case 2, if n is equal to minus 1, then of course, you cannot have n plus 1 in the denominator, but firstly the integrand is just 1 or sorry, it is just okay. So, the integrand is 0 to 2 pi minus r power n plus 1 times 0 for the real part, because sine of 0 is 0, okay, and then plus I times integral 0 to 2 pi r power n plus 1 times cosine 0, which is 1 dt. Okay. So, that you get r power n plus 1, well, n is minus 1. So, I can substitute r power 0. So, I just get 1 here, 1 times I times 2 pi. So, which is 2 pi I. Okay. So, the contour integral f of z dz, where the contour is a circle of radius r centered at 0, okay, and f is z power n is equal to so, let me write z power n instead of f. Z power n dz is equal to 0 if n is not equal to minus 1 and it is equal to 2 pi I if n equals minus 1. Okay. So, this is very important integral, this is a fundamental integral, okay, and we can actually, there is another form of this, we can actually extend this to the following, and this is an exercise to the viewer. Let r be greater than 0 like in the previous example, and a be any complex number, a be a given complex number, okay, and let gamma of t is a plus r e to the I t 0 less than or equal to t less than or equal to 2 pi. Okay. Then show that the contour integration of the function z minus a power n dz is 0 if n is not equal to minus 1 and 2 pi I if n is equal to minus 1. Okay. So, this is an extended fundamental integral. Okay. So, it is very useful and important for us. Gamma is a circle of radius r around a point A, okay. R is any positive number. Then the contour integration of z minus a power n has exactly two values, 0 or 2 pi I. Okay. So, that is an exercise, okay. And now, we have some properties of this contour integral, some easy properties and then some properties that we will prove. Okay. These easy properties are quite easy to see, so I will not prove them. Okay. The first of them I want to say is that the okay. So, I have to state my assumptions. Let gamma be a contour, okay, with parameter interval a b, then and let f and g from gamma star to c be continuous, okay, and okay, then firstly the contour integral over gamma of f of z plus g of z, okay, actually plus or minus g of z, okay, dz is the contour integration of f over gamma plus or minus the contour integration of g over gamma, okay. This is something we expect, okay, and to prove it is very easy, just use the definition of contour integration, okay, and likewise if you have a constant times f of z dz, okay, and you want to do the contour integration, the constant can scale out of the contour integration, okay. This is gamma, okay, for any a belongs to C. So, if A is a constant like that, it scales out of the contour integration. Okay. Next, okay, so now suppose that, so here I want to state further properties in a lemma. Okay. So, suppose that gamma is a path with path or a contour. Okay. So, I am saying contour. So, I will just say contour, okay, with parametric interval a comma b, okay, and let f from gamma star to c be continuous like above. Okay. Then we have three properties. Okay. The first one is that the integration over minus gamma, remember what that is the opposite path to gamma of f of z dz, the contour integral of f over the path minus gamma is the negative of the integral of f over gamma. Okay. So, that okay, that tells us, or that is the motivation for why we named that opposite path as minus gamma. Okay. So, so it is the first property, and the second of the properties is that suppose that a is strictly less than tau is strictly less than b. So, tau is some value between a and b. Okay. Let gamma 1 be the restriction of gamma to the closed interval a tau, okay, and gamma 2 be the restriction of gamma to the interval tau b. Okay. What that means is that you just define gamma 1 of t equals gamma of t, okay, on the interval a comma tau. You do not care for the definition of gamma 1 outside of this interval a comma tau. Okay. So, likewise gamma 2 is gamma of t on the interval tau b. Okay. And then the integration, the contour integration of f of z on gamma, okay, is actually equal to the contour integration over gamma 1 of f of z dz plus the contour integration of f on the contour gamma 2. Okay. So, you can take a parametric interval and split it up into pieces and restrict the original curve to each of these pieces and find the contour integral on each of these pieces and add up to get the original contour integral mind you, you can only slice the interval into finite number of pieces, okay, not okay. So, so in this case we just split it up into 2 pieces, okay, and it works. So, that is the second part of this lemma, okay. And the third part of this lemma is that if you have, so if you have what is called a reparameterization of a contour, okay. So, let gamma tilde be another path, okay, with parameter interval c comma d, okay. Suppose that gamma tilde is gamma circle psi. So, it is the composition of psi with gamma, okay, where psi is a function which maps the interval C D to the interval A B, okay, and has a positive continuous derivative. Okay. So, psi is a function, okay, from C D to A B. It is a real valued real variable function, okay, and psi prime is a continuous function, and also psi prime is always positive. That means, psi is an increasing function, okay, and not only that, it is also 1 to 1, okay, it is a bijection actually, okay, and it is a smooth function, it is a smooth bijection from C D to A B, okay, and it is invertible as well. Okay. So, automatically the inverse function will be smooth as well, okay, smooth according to the definition, restricted definition we gave, okay, and then the integration of the contour integration of f on gamma will be the same as the contour integration on gamma tilde of f. Okay, so, that is the conclusion. Okay. So, what this reparameterization really is that you take a contour, okay, and then you look at its range in the complex plane. So, it is a curve of certain sort, and then it has a range. You try to come up with yet another smooth function, smooth curve, such that the range is the same. Okay. So, to quickly exemplify, you look at gamma of t, okay, equals let us say t plus I t. Okay. So, this looks like this starts at 0 and ends at 1 plus I. Okay, that is the range of this function, 0 less than or equal to t less than or equal to 1. Okay. And you could also look at gamma tilde of t equals t squared plus I t squared. This is just a motivational example. Curves can be much more complicated, of course, contours can be much more complicated. So, 0 less than or equal to t less than or equal to 1. Okay. Then gamma tilde is a reparameterization of gamma, okay, because you can easily construct a function psi, okay, from 0 1 to 0 1, such that gamma tilde is gamma circle psi, okay, and what might that be? Psi of t is t squared. Okay. Psi of t is t squared. Okay. So, gamma tilde is gamma circle psi. Okay. That is clear to, that is easy to verify. So, then this gamma tilde is a reparameterization. So, you can describe that particular curve you see, okay, the range of gamma that you see, you can reparameterize it in terms of some other function, okay, and then there will you can possibly come up with such a function, okay. And when you can, the lemma says that the contour integral of f tallies with the contour integral of f on gamma tilde, okay. So, so this is very neat, because then now it turns out that the contour integral really depends only on the range of gamma, okay, namely the gamma star, and not on how you parameterize it, as long as gamma satisfies some smoothness conditions, etc. Okay. So, under very mild conditions, your integration, contour integration is really a property of the range gamma star. Okay. So, having said that, we will see the proof of property 3 in this lemma. The proof of property 1 and 2 are exercises. They are fairly easy. One has to use the definitions of a contour integral. Okay. So, 1 and 2 are left as exercises for the viewer. Let us try to see the proof of property 3 here, okay. And it is as follows: proof of 3. Okay. So, gamma tilde, okay, is gamma circle psi, okay, gamma tilde of t, okay. So, suppressing the t here, okay. And since psi is differentiable, gamma is differentiable, the composition is differentiable, and so gamma tilde prime of t, okay, by using the chain rule, is gamma prime of psi of t, okay, times psi prime of t. That is the chain rule, right. So, using the chain rule, you get this, and we will use this to do the following. So, the contour integral over gamma tilde of f of z dz is, by the definition, c to d, that is the parameter interval for gamma tilde, okay, of f of gamma tilde of t times gamma tilde prime of t dt. Okay, that is the definition of, that is by the definition of contour integration. Okay. And gamma tilde of t and gamma tilde prime of t are here. So, I am going to substitute them in here. Okay. So, this is integration from c to d of f of gamma circle psi of t. So, gamma circle psi of t is gamma of psi of t. Okay, that is the definition of composition, and then gamma tilde prime is gamma prime of psi of t, psi of t times psi prime of t dt. Okay, at this stage, I have eliminated gamma tilde and brought in gamma, just using the definition, or just using the equality right here. Okay. And then now I will make a substitution, let tau be equal to psi of t. Okay. So, that d tau is psi prime of t dt, okay. And when t equals c, tau is psi of c, which will be a, okay. And when t equals d, for the upper limit of integration, tau will be psi of d, or rather psi of d, which will be equal to b. Recall, psi is a monotone function, a monotonously increasing function, okay, and it maps a to c to a and d to b. Okay. So, then the contour integration over gamma tilde of f of z dz will equal, with this substitution, it will equal the integration from a to b. Now, we will write everything in terms of tau. So, you get f of gamma of tau, because psi of t is tau now, okay, and then gamma prime of psi of t is tau, and psi prime of t dt is your d tau. Okay. And this now exactly looks like, well, it is the contour integration over gamma of f of z dz. Okay, and that proves that these two integrals are one and the same. Okay. So, with that we can really talk about computing contour integrations on a certain contour spoken of as curves in the complex plane, or as ranges in the complex plane. Okay. So, here is an example. Okay. So, compute the contour integral of z squared dz, where gamma is a contour formed by joining gamma 1, the interval minus r comma r, okay, and gamma 2, which is r e power I t 0 less than or equal to t less than or equal to pi. Okay. So, compute the contour integration, okay, where only the range of gamma 1 is given. So, here is your minus r, here is your capital R, okay, and r e power I t is the semicircle in the counterclockwise direction, okay, and this is your gamma 1. And this is your gamma 2, okay, and this is the join. Okay. So, if you observe the parameterization of gamma 1 has not been given to us, it is just it can be parameterized in any way you please, owing to the lemma property 3 of this lemma above. Okay. Because any way you parameterize, or any smooth way you parameterize gamma 1 is going to give you the same result. Okay. So, so the contour integration over gamma, okay, of z squared dz. Okay. Well, let us first write a parameterization for gamma 1. Gamma 1 can be described as minus r times 1 minus t plus r times t. Okay. So, so then we are almost all set. Okay, I am saying almost for a reason. The integration to compute the contour integration of z squared dz over the contour gamma. Okay. So, now if I can split this into, well, gamma is the join of gamma 1 and gamma 2. Okay. So, it would be nice if I can split this into the contour integration over gamma 1 plus the contour integration over gamma 2 of z squared dz. Okay. So, so let us see that one can indeed do this when gamma 1 and gamma 2 are smooth at least. Okay. So, here is a proposition. Okay. So, like in the above lemma, let gamma 1 and gamma 2. So, let gamma 1 be a smooth curve, okay, with parameter interval a b, okay, and let gamma 2 be a smooth curve, with a parameter interval c d. Okay. Then okay, and let f from gamma 1 star union gamma 2 star, okay, to C be a continuous function, okay, where gamma 1 of B is equal to gamma 2 of C. So, what that means is that the end point of gamma 1 is equal to the initial point, the final point of gamma 1 is equal to the initial point of gamma 2. So, that I can form the join of gamma 1 and gamma 2. Okay. Then the conclusion is that the contour integral of f on the join of gamma 1 and gamma 2 is indeed equal to the contour integral of f on gamma 1 plus the contour integral of f on gamma 2. Okay. And the proof involves the fact that you can shift the parameter interval and yet get the same value of the contour integration. Okay. So, recall gamma 1 plus gamma 2 is defined in a certain way. You go from A to B for gamma 1, okay, and you go from B to not exactly D, but you go until D plus B minus C, okay, for tracing gamma 2, where gamma 2 is T minus B plus C. Gamma 2 and the parameter for gamma 2 will be T minus B plus C. Okay. So, there is a shift here, we shifted the interval C D to B comma D plus B minus C. There. So, we have made a shift, and but we have anyway balanced for that using this parameter T minus B plus C. Okay. So, that will take care of that, and you can show that using the definition of contour integral, you can show that this turns out. The first piece is not a problem, okay, but the second piece turns out due to this balancing act. Okay. So, that is easy to prove, that is left to the viewer as an exercise. And next I want to talk about a fundamental theorem of calculus for complex integrals, for contour integrals of this sort. Okay. So, the fundamental theorem of calculus. Okay. So, here is the theorem, statement of the theorem. Okay. So, suppose that gamma is a path or a contour, okay, with parameter interval A comma B, okay, and that capital F is defined, okay, on an open set containing gamma star, okay, and that f prime of z, okay, exists and is continuous at each point of gamma star. Okay. So, then the contour integral over gamma of f prime of z dz is equal to f of gamma of B minus capital F of gamma of A, if, okay, in general, okay, and 0 in particular when if gamma is closed. Okay. So, there is no real need of bifurcation. If gamma is closed, gamma of B is equal to gamma of A. So, that subtraction is automatically 0. Okay. So, this is the fundamental theorem of calculus in this context, and we will see a proof of this. It is really easy. So, assume that gamma is smooth to begin with. Okay. So, we will relax this for the time being. Let us assume that it is smooth. Okay. So, now the hypothesis on f that it is differentiable on an open set containing gamma star allows us to say that so f circle gamma, okay, is differentiable. Notice f circle gamma, it is a function from this interval parameter interval a b to the complex plane. So, f circle gamma, note f circle gamma is a function from the parameter interval a b to the complex plane, okay, and it is a composition of a smooth function or a smooth function and a differentiable function. So, it is differentiable, of course. Okay. So, let us compute the derivative using the chain rule. F circle gamma prime of t, okay, is equal to f prime of gamma of t. F prime exists at every point gamma of t. Okay. So, it is f prime of gamma of t and then times gamma prime of t. Gamma is smooth by assumption. Okay. So, gamma prime exists as well. So, that is the derivative. Okay. So, in order to compute the contour integral gamma f prime of z dz on the contour gamma. So, we need to use the definition. This is integration from a to b of f prime of gamma of t times gamma prime of t, okay, dt. But the integrand is nothing but the derivative of f circle gamma of t. Okay. So, this is the integration from a to b of f circle gamma prime of t dt. Okay. So, f circle gamma is a function from the interval a b to c and it is differentiable. Okay. So, the derivative and the derivative is continuous as well. So, the derivative function here is being integrated. Okay, and we define this kind of integral to be the integration of the real part of this function f circle gamma prime of t, which is a continuous function, okay, dt plus I times the integration from a to b of the imaginary part of f circle gamma prime of t dt. That is the definition of an integral of this kind. Excuse me. So, so that is by the real fundamental theorem of calculus, the fundamental theorem of calculus for real functions. This is nothing but the real part of f circle gamma of t, okay, and between the limits a and b plus I times the imaginary part of f circle gamma of t, excuse me, between the limits a and b. Okay. And when we add, of course, we get f circle gamma of t, okay, between a and b. Okay. So, that is f of gamma of b minus f of gamma of a, okay, and that proves the theorem. Of course, when gamma is a closed curve, well, let me add something, but when gamma is a closed curve, of course, this difference is 0 because gamma of b is equal to gamma of a. Okay. If gamma is piecewise smooth, okay, all you have to do is split this contour integration, like one of the properties in the lemma we have seen earlier. We have to split this into pieces k equals 0 to n minus 1, the integration from t k to t k plus 1, okay, of f prime of gamma of t, gamma prime of t dt, where gamma restricted to any of these intervals t k comma t k plus 1. So, it is piecewise smooth. So, you can separate the interval parameter interval a b into pieces such that it is smooth on each of these pieces. Okay. So, and these are finitely many pieces. So, what I am doing is adding up the integrals on those pieces. Okay. And now, you can apply what we have done before. So, apply previous to what we have done before to each of these t k plus 1 f prime of gamma of t, gamma prime of t dt. Then what you get is a telescoping kind of sum, okay, and you end up with f of gamma of b minus f of gamma of a. Okay, so, that piece I will leave it to you, that is easy. So, that is the end of this proof. Okay.